All right, let's talk about one of the most important parts of graphing sine and cosine functions, the vertical shift. You know how these waves move up and down. We're going to break it all down, and I'm going to show you the one secret starting point that makes graphing these things, honestly, a whole lot easier. So let's dive in.
So you see an equation like this. And yeah, it can look kind of messy. You've got a negative sign, a number out front, a number tacked on at the end. It's really easy to feel a little lost. But what if I told you there's one single starting point that makes everything else just click into place?
You see, the key isn't the amplitude or how stretched the wave is. The real secret, the first thing you should always look for, is its new home base, its center line. We're going to call this our secret axis, and I promise you, once you find this, everything else gets so much simpler. So how do we find this secret axis? Well, it's actually super simple. In the general form of the function, you know that number that's just added or subtracted at the very end? We call that the d value. That number is the vertical shift. If d is positive, the whole graph moves up. If it's negative, the whole thing moves down. That's it. That one little number controls all the up and down movement.
And this leads us to our secret weapon, the sinusoidal axis. This is just a new horizontal line that we're going to draw right at whatever y equals d is. Think of it like this. The original sea level for a wave is the x-axis, right, at y equals 0. But our new shifted wave has a new sea level, a new center. And this line is it.
So here it is. This is the big one. This should be your mantra, the very first thing you do every single time you see one of these problems. Find the axis first. Before you even think about amplitude or reflections or anything else, find and draw this new axis. It's what anchors the entire graph. To really see how this works, let's start with the basics. Here's our standard y equals sine of x. See how it's perfectly balanced on the x-axis? It goes up to 1, down to -1. But its midline, its sinusoidal axis, is right there at y equals 0. This is its natural home.
Okay, now let's actually do the shift. Say we have the function y equals sine of x plus 3. Our d value is a positive 3. So, what's our mantra? Find the axes first. We're going to go straight to y equals 3 on our graph and just draw a new dashed line. That's our new home base.
And now for the magic. We take that original sine wave and we just lift it straight up. The entire wave is now wiggling around that new axis we drew at y equals 3. Nothing else has changed. It hasn't been stretched, it hasn't been flipped, it's just been moved. Simple as that. All right, so now that we've got the secret, let's go back to that kind of scary-looking problem from the beginning. We're about to see just how easy it becomes when we use our step-by-step process. Okay, let's break down y equals -2 cosine of x plus 3. Step 1, you know the drill, find the axis. The d value is plus 3, so boom, we draw our new midline at y equals 3. Next, we look at the amplitude, a. That's just the number out front, so it's 2. This tells us our wave is going to go 2 units up from our new axis and 2 units down from it. Then we check for reflections. See that negative sign in front of the 2? That tells us the whole graph is flipped upside down. A normal cosine starts at a maximum, so ours is going to start at a minimum. And finally, we just plot our key points for one cycle using our new axis as the reference. So let's put it all together on the graph. First, we draw our axis at y equals 3. We know it's a reflected cosine, so it's going to start at its lowest point on the y-axis. With an amplitude of 2, that minimum is 2 units below our axis. So it starts at y equals 1. The maximum will be 2 units above our axis, way up at y equals 5. From there, we just plot the rest of our points and connect them with that nice, smooth curve. And just like that, the complex graph comes together perfectly.
Now, before we go any further, I have to point out a really common mistake. With these transformations, the order you do them in matters a lot. It's just like order of operations in arithmetic. If you do it in the wrong order, you can get a completely different graph.
Let's just look at this. On the left, we're doing it the right way. Stretch first, then shift. We take sine of x, we stretch it by 2, and then we move it up by 1. Our final axis is at y equals 1. But look what happens on the right if we get the order wrong. We shift sine of x up 1 first, and then stretch the whole thing by 2. That means we have to distribute the 2, and we end up with y equals 2 sine x plus 2. Now our final axis is at y equals 2. These are 2 totally different graphs, and it's all because of the order. So the takeaway here is super clear. You have to perform the transformations in the same order as the order of operations. Always do your stretches and reflections first, And then, after all that, apply your shifts. It is the most reliable way to get the right graph every single time. All right, let's flip the script. What if, instead of an equation, you're just given a finished graph and you have to figure out what the equation is? Well, our little secret still works. We just use it in reverse.
Take a look at this graph. It's obviously a sine or cosine wave, but its midline is definitely not the x-axis. So how do we figure out its equation? You already know the answer. What's the mantra? Find the axis first.
So how do we find the axis just by looking at a graph? Simple. We just find the highest point and the lowest point and figure out what's exactly in the middle. Here, the max is up at y equals 3, and the min is down at y equals -1. What's smack dab in between 3 and -1? It's 1. That's it. Our sinusoidal axis is at y equals 1, which means our d value is 1.
Okay, now that we know our axis is at y equals 1, finding the amplitude is easy. We just ask, how far does the wave go from its midline to the top or bottom? Well, from 1, it goes up to 3. That's a distance of 2. And it goes down to -1. That's also a distance of 2. So our amplitude, A, is 2. Last piece of the puzzle. Let's look at where the graph crosses the y-axis. It's at a minimum point. Now, we know a normal cosine function starts at a maximum, and a sine function starts right on its midline. So if it's starting at a minimum, it has to be a reflected cosine function. So let's put it all together. It's a reflected cosine, the amplitude is 2, and the vertical shift is +1. The equation has to be y equals -2 cosine of x plus 1.
So there you have it. It doesn't matter if you're starting with an equation and graphing it, or looking at a graph and trying to find the equation. The strategy is exactly the same, and it all comes back to that one simple core idea. For any vertical shift, the secret is always find the axis first.
So now you have the key. You can handle any vertical shift that gets thrown at you. You can move these waves up and down with total confidence. But that brings up the next big question, doesn't it? We've mastered up and down, so what's the secret to moving the wave left and right? That's something we'll explore next time.